This video is on exponential models. An exponential model has a variable in the exponent or the power. It can represent exponential growth or exponential decay. All exponential models have a horizontal asymptote which a curve approaches on one side. So these two graphs here, the first one shows exponential growth and the second one shows exponential decay. Now in an exponential model, it looks like this. And you can see there the x is in the power, which is what I said before. The variable is in the power for it to be an exponential model. Now just some things to note about this model. If the r value is positive, then it's an exponential growth. So if the power is positive, it's growth. If that power there is negative, it is a decay. The horizontal asymptote is when y equals c. So that's on the graph, that's that red line where the graph approaches. Remember, it never crosses that line. With the y-intercept, there's two ways you can find that out. So if you remember this, the y-intercept is also k plus c, so that number in front at the front and plus c. Obviously for the y-intercept you can also sub in when x equals 0, which is what the next point is, because the initial value is when x equals 0. Often they ask in these types of questions for the initial value. So you can either remember the k plus c or just sub in 0. Long-term behaviour refers to the value of y when x is large, so as x is getting bigger and bigger or smaller and smaller. It just links to the horizontal asymptote, and quite often that is the solution. First example, sketch the function y equals 10 times 3 to the power of negative x plus 2, labelling the intercept and the asymptote. So first of all, we see it is a negative power, which means it is an exponential decay, which means the graph is going to be going down like that when we draw it. To draw this, we also need to know the y-intercept and the asymptote. So the y-intercept, remember, you can either do the k plus c if you remember that, or you can make x equal 0. So if we make x equals 0, we have y equals 10 times 3 to the power of 0 plus 2. Remember, anything to the power of 0 is just 1, so it'll be 10 plus 2, which is 12. And you see there we've done the k plus c. It's just most of the time people forget that you can do that, so it's just easier to put x as 0. So our y-intercept is at 0, 12. And then the asymptote is just whatever value is added or subtracted to the exponential, which in this case it is plus 2. The asymptote is when y equals 2. And then we just graph it. Now with this, it does say sketch, so it doesn't have to be perfect. So if I'm going to say that here is 2, we'll say that there is 12. We know at 2, that's where the asymptote is going to be. So our line can't cross that, and we just draw the graph. So we know it's going to go down and across like that. And then it wants us to label the intercept as well, so you'll probably label it like that. And the asymptote, just drawing that dotted line is enough. Next question, an exponential model has the form y equals k times 2 to the power of x plus c. It passes through 2 points, 1, 4 and 2, 10. Find the value of y that the model predicts when x equals 4. So we're wanting to put 4 into this equation and work out what y is. Our only issue here is that we don't know what k and c are. So we need to work them out first. But luckily we've been given 2 points and we need to find 2 variables, which should be in our minds linking to simultaneous equations. So if we look at the point 1, 4, sub that information in, we get 4 equals k times 2 to the power of 1 plus c, which we can simplify to 4 equals 2k plus c, and then we have the point 2, 10. Sub that in and we get 10 equals k times 2 to the power of 2 plus c, which simplifies to 10 equals 4k plus c. Now we have 2 linear equations and you can solve that on your calculator. Remember, simultaneously you can use the simultaneous solver function, or you can graph them both and see where they intersect. When you solve this, you will find that k equals 3 and c equals -2. which means our actual equation is y equals 3 times 2 to the power of x minus 2. Now we can predict what y would be when x is 4. We just need to sub 4 into the equation. So y equals 3 times 2 to the power of 4 minus 2. Put that in your calculator and you'll get an answer of 46. Last example, this is more of like a question you would see in an exam situation. The temperature of a kettle, which is in T degrees Celsius, at a time of T minutes, after it has boiled, is modelled by this equation. T equals 80, e to the power of a negative 0.1 T plus 20. Part A, what is the initial temperature of the kettle? B, what is the temperature after 10 minutes? C, how long does it take the kettle to cool to 30 degrees C? And state any assumptions, deduce the temperature where the kettle is kept. So part A. What is the initial temperature? Remember, initial temperature is when time is 0. So we just sub time is 0 into the equation and you will get 100. So the initial temperature of the kettle is 100 degrees Celsius. Part B, what is the temperature after 10 minutes? We now just need to sub in 10. With a question like this, just check what the time units are. In this, T is in minutes, which means we don't need to convert that 10 to anything, which means we'll have T equals 80 e to the power of negative 0.1 times 10 plus 20. Put that into your calculator and you will get that T equals 49.4 degrees Celsius to 3 significant figures. C, how long does it take the kettle to cool to 30 degrees C? So now we know the temperature at the end and we're trying to find what the time is. So it'll be 30 equals 80 e to the power of a negative 0.1 T plus 20. With this you can just put it in and solve it and it will tell you that T equals 20.8 minutes. And the last one, part D, stating any assumptions, deduce the temperature the way the kettle is kept. So this is very typical type of those last question, the last parts of questions asking you to think about the context of the question and how the equation is built up to really test that higher level of understanding. So with this, some assumptions that we can make. The main one is that we can assume that the model can be applied until the kettle cools fully. And from that then, because it's a long-term thing, that long-term behaviour, we look at what the asymptote value is. And in this equation, it is 20. So that means that's what the equation is going to. That is, it's a decay. It's approaching the asymptote is that temperature, which is 20. So we can assume then that the temperature of the room where the kettle is 20 degrees Celsius. And we can just say to 20 degrees Celsius. But the reason for that is because that is the asymptote. And that is exponential functions.